Hello and welcome to the Swift Tuition YouTube channel. In this video, we'll be covering the following topics: average gradients, the limits, and first principles in the context of calculus. Here are ways in which you can contact us. So you could message us and send us a DM on Instagram, or you could message us on WhatsApp, or you could email us, first to being the preferential means of contacting us. Okay, so in this video, we'll be obviously dealing with these three topics in calculus, as they will be your primary introduction to differentiation, first and foremost. And differentiation is the process of finding the derivative. So in this video, we'll be dealing with how to find the derivative using first principles. That's the focus. Alright, so before we talk about first principles, we first want to introduce the concept of the average gradient. So you may be familiar with the term gradient itself, right? So in order to find the gradient, we'd find the change in y over the change in x, y2 minus y1 over x2, should say x2 minus x1 over here. So y2 minus y1 over x2 minus x1, right? So that was the way in which we would find the gradient, or in other words, the slope of a linear function. So I would take these 2 points and I'd find 5 minus 2 over 2 minus 1, right? But what if the function wasn't linear, right? So whenever we're dealing with the slope or gradient, we're typically dealing with the straight line. So in cases where the line is not straight, what we can do then is find the average gradient. In other words, the average rate of change. Gradient is related to the average rate, or to rate of change, right? So what is the average rate of change? What is the average rate of change? Well, then we'd find m of ab, right? And then we find delta y over delta x. 5 minus 2 over 2 minus 1 is equal to 3, right? So that is how we'd find the average gradient. So it's just normally finding the gradient, but now it's average because it's not a straight line anymore. We're dealing with a curve of sorts. So with that information, we can derive a general formula for the average gradient, right? So let's assume that a point A, is called x, right? And then normal function notation, if this point is called x, then the y value associated with that x value would be called f of x, right? So now, obviously, that means that x at this particular point is just called x, right? But what if I add a certain distance of h? So let's say it was 1, and then I added a distance of 2. Well, then this would be 1 plus 2, right? In other words, x plus h to generalize, right? So now I've got x, and I've got another x value of x plus h because I've added a certain distance of h. So now let's look at the y value associated with that. Well, you can see it's point B over here. So I've got x plus h. What is the y value associated with x plus h? Again, function notation. If the x value is x plus h, then the y value associated with that would be f of x plus h. So now I can just do the same gradient formula that we dealt with in the previous slide, but now what we're then going to do is we're going to use it generally. So f of x plus h, because h could be anything, x could be anything. F of x plus h minus f of x, right? And then x plus h minus x. So we simplify that, and then we find that the x's will cancel out, and then we're just left with an h. So this is how we find the average gradient. This is the general formula. So the distance between the two x values, and then the difference between the y values. So the distance between the two x values is obviously just h. You can see that's the distance between the two x values, and then the distance between difference between the two y values is f of x plus h minus f of x. Now, like I said before, a gradient tells us how far something is changing, right? So before we're finding the average rate of change, in other words. So in other words, the gradient gives us the rate of change. In the previous parabola, we found the average rate of change. But what if we wanted the gradient at a single point? So over here, there was a distance of h. What if I just wanted the gradients at a single point? So I don't want a distance of h whatsoever. I just want at a single point. How do I find the instantaneous rate of change? So let's look back at this equation. So remember how h was the difference between the x values, right? So now what we're then going to try and imagine is that h getting smaller and smaller and smaller to the point where it's practically non-existent or negligible, or to a point where it's practically equal to 0, right? So that's where we introduce the concept of the limit. What is the limit? In grade 12, you only need to understand the limit as the y value that a function approaches the closer our x or h values get to a certain number. Let's have another look at our parabola. All right, so as you can see, h1 is less than h2. Here's h1, the distance between a and b. That is smaller than the distance between a and c, right? Now, the x values of a and c, respectively, right? So you can see that if I were trying to find the rate of change, the instantaneous rate of change at the specific point A, right? I would then, you can see that this b value is a little closer to what point A is doing than this. Well, basically the average gradient of AB is closer to what I'm looking for as opposed to the average gradient of AC. So I just have to keep making this value smaller and smaller and smaller. I need to keep making H smaller and smaller and smaller, right? Therefore, if H was actually 0, we could actually hypothetically calculate the gradients of the curve at the single points. Now, there's a problem that arises, and the problem that arises is the fact that H can't really be equal to 0 because we know that we can't divide a number by 0. So that is why we introduce the concept of a limit. So the limits kind of allows us to sort of bypass the fact that the denominator cannot be equal to 0. Right, so in the parabola above, the line at A is now a tangent. Alright, so you can see over here, it's basically what I've just done over here. It's basically this particular thing, except now we're no more dealing with points A and B or points A and C. We're dealing with just the line that touches A exactly, right? So no crossing the lines or whatever, no crossing the curve. So it's a gradient, right? I'm not sorry, it's a tangent. It's a tangent. So over here you can see it's just a tangent. It just touches at point A. That is the only point where it touches, right? So now this would give me the instantaneous rate of change. In the parabola above, the line at A is now a tangent. We now no longer have to speak of the average gradients across 2 points, but can now find the precise gradients of the function at point A. In other words, the instantaneous rates of change at point A. Alright, so now assuming the equation of the parabola is f of x is equal to x squared plus 1, so this is this particular parabola over here, we know the f of x plus h is equal to, right, so now when you're dealing with this type of thing, right, you can see that it's basically the same equation, f of x plus h minus f of x, right, and then there's an h over here. So I'm still using this equation because it's still basically a gradient, except it's the instantaneous rate of change, right, the instantaneous gradient, the gradients at a singular point. All right, so we're still dealing with the gradient, so that's why we're still using the equation fundamentally. We're still, this thing basically still comes from the whole f of x plus h minus f of x all over h. Alright, so this thing, f of x is equal to the limit as h tends to 0. This is basically what I just have over here. F of x is equal to the limit as h tends to 0. You can see there are a bunch of numbers over here. This is basically just this, f of x plus h minus f of x all over h. I've just done the additional step. So what you basically do, and you know this is how we deal with this, is that when you're talking about f of x plus h, we're talking about it's basically y is equal to mx plus c, y is equal to ax squared plus bx plus c, etc. It's basically just an equation, right? So I just took this thing, right, x squared plus 1, right, and then we know that wherever we have x, we then replace it with x plus h. So that's what I've done over here. So I've just taken all of the x's in this original f of x function and I've replaced it with x plus h. So x plus h squared plus 1. So I've just replaced x plus h where there's the x over here, x plus h all squared plus 1, and then I've got x squared plus 2xh plus h squared plus 1. So now that's what I've got over here, right? And I can just simplify that, and now I need to subtract that with f of x. So what is f of x? This is simply f of x. So I like to do the f of x plus h separately, just so I'm not doing everything on the singular line. So just isolate f of x plus h first, calculate that, and then f of x is just the original function you're given. So this is f of x, obviously, right? So I just take this, because everywhere I see an x, I just replace it with an x. Obviously that does not change. As opposed to here, so everywhere I see an x, I replace it with an x plus h, x plus h, x plus h, x plus h, and I multiplied it out, and then I've got this thing. So I've written it here, and then yeah, and then we simplify, we cancel out, and then we can see that now this h can kind of be cancelled out. So we've kind of bypassed the fact that the denominator cannot be equal to 0. So I've cancelled out the h, so now I've got something like, at the numerator, in the denominator, now I've got 2x plus h. The limit says h tends to 0 of 2x plus h. Once you reach this stage over here, then you can just substitute h into this thing, 2x plus h, and then everything drops. And then the limit is h tends to 0 drops. So you don't have to write, you don't write that anymore. So now it's just 2x plus 0 is equal to 2x. And then this is the instantaneous rate of change. So the gradients of the tangents at this specific point of A. And alright, so this thing here just gives us a very general gradient for anything that lies on this function. So we're just taking the original function, and then we found the gradients of any line that could lie on this function. You can see that there's a variable over here, which means that at this particular point, the gradients of the tangents at this point is not going to be the same as the gradients of the tangents at this point, right? It's not going to be the same as the gradients of the tangents at this point. The gradients of the tangents will vary depending on where it is, right? So here I've got 2x plus 0, and then obviously that just leaves me with 2x, right? So there's 2x, and I just replace the x with whatever point I'm dealing with. In this particular case, I'm dealing with 1 over here. So I'm going to put 1 into the function. So now I've got 2x, 2x, right? This is the general first derivative for anything, any gradient that any gradient of the tangent that lies on this line. But what if I want a specific tangent? Well, then I just use the x value associated with that tangent. So the x value associated with the tangent of A is obviously the tangent that passes through A is obviously 1. So I'm going to replace 1 over there. And then I've got 2 multiplied by 1. And then I find that the first derivative is equal to simply 2, right? You may probably know the first derivative at a turning point. You can see here's my turning point. And then what would the first derivative at a turning point be? If you already know this, then you know that the first derivative should be equal to 0. Now let's check that with our equation over here. What's 2 multiplied by 0? Well, that'll just be equal to 0. So the first derivative of it at a turning point is going to be equal to 0. In much the same way, if you look at anything to the left of this, then you can see that the gradients of the tangents are all going to be negative. And you can see as well that they all lie on the negative x side, right? So if you were to substitute any negative value over here, you would see it would always give a negative value. And that makes sense, because what the first derivative really is the gradient of the tangent to the curve, right? You can see that the gradient of this the tangent to this curve is equal to is positive, right? So the first derivative makes sense for the first derivative to be positive. We know that the gradients of a horizontal line, right? The gradients of a horizontal line like this would simply just be equal to 0. That makes sense. A horizontal line has a gradient of 0, and then that therefore makes sense when you're dealing with the gradients of the tangents to the curve. In other words, the first derivative, and the first derivative is going to be equal to 0. Alright, so let's try a question in this context. Use differentiation from first principles to find the derivative of f of x is equal to x squared plus 6x plus 9. So as soon as you see from first principles, you know that we have to whip out our formula. The formula reads the first derivative, or f dash x of f dash x is equal to, the limit as h tends to 0 or h approaches 0 of the function of f of x plus h minus f of x all over h, right? So we're going to be looking essentially to what y value is being approached. The closer our h gets to 0, the smaller our distance between f of x plus h and f of x becomes, what is the y value that we approach to. So this is obviously the general formula. Now I want for this specific equation. So let me find for the specific equation. And the way I like to do that first is to isolate f of x plus h. Remember, x plus h in the middle here means that everywhere where you see x in the original function, you replace it with x plus h. So let me do that. Right, so you see I've kept everything else in the function the same. All I've done is everywhere I see x plus h. 6x, x plus h, and then the 9 obviously remains the same. So multiply everything out. So that'll obviously be x squared plus 2xh plus 6x plus 6h plus 9. So I've multiplied everything out. See if there's anything you can simplify over here. There is not. So what I then do is I take all of this and then I can plug it now into this thing. All right. Okay. So now what I've done is I replaced f of x plus h with f of x plus h. This is basically f of x plus h just written in other words, right? Then I now have to replace this thing with f of x, all right? Because this is what f of x, this is where I put f of x. So f of x is just the original function. So instead of x plus h here, it's going to be x squared plus 6x plus 9. All right, so when you're substituting inside, make sure you put it in brackets first, because that makes a very big difference because of this minus sign. This minus sign is minusing this entire f of x. So if you don't put the minus sign, outside of this thing, if you don't put everything else in brackets, what you then only be doing is maybe the minus sign minus the first term, the minus sign of the first term. That's all you'll be doing. But remember, the minus sign is for the entire f of x, and this is f of x. So make sure that you keep it in brackets first. And then once you've multiplied the minus sign into the thing, only then can you remove the brackets. So I'm just going to do it all in this line. So if I were to find the minus version of everything, then minus x squared is obviously just minus x squared, right? And then I had 6x, so minus times 6x would just be minus 6x, and then that'll be minus 9. So I'll just multiply whatever is inside the brackets. That's all I've done. Now what you can then do at this point is you're looking for like terms that we can cancel out. That is our objective now. So we need to try and find like terms that we can cancel out, because the objective, the end goal, is to be able to remove this h from the bottom. That's what we're trying to do. We're trying to use our algebra to remove this h from the bottom. We do not want it, right? Because we can't find the first derivative without this, with this h over here, because obviously we can't divide by h. All right, so is anything we can cancel out? There's 6x over here. I cancel with the 6x over there. There's an x squared over here, and I cancel out with the x squared over there. There's a plus 9 over here, so x squared minus x squared, right? And then that was positive 6x minus 6x. There's a positive 9 over here, and then there's a minus 9 over here. And I'm just left with 2xh and then 6h over here, and that's perfect. I love that, because I know I can take out an h over there, and then I can cancel out from the bottom and the top. So now I have this thing going on, right? So I've just taken these two terms, and I've just taken out a common factor of h, and then I've obviously left everything the same. So yeah, that's all I've gotten over here. I know I can cancel this out, and then I'm left with the limit as h tends to 0 for 2x plus 6. So yeah, so now this is what I'm left with, right? And then as you can see, there is no h, right? But if there was an h, I would substitute. If there was an h in the denominator left, I would substitute anywhere with an h with a 0, right? The objective was first to just cancel out this h at the bottom over here. I've done that, so I'm cool, right? So I cancel out this this h with a 0. That's what I'm going to do now. So I've canceled out the h's, right? And I'm basically, there's no h, but if there was, I would have substituted the 0 into that h, right? In this particular case, there isn't, so I can just take this particular thing, and I can just drop everything, right? So now I've got 2x plus 6. Right, so now this will be my first derivative. Then I can have f of x, right? So we keep this limit as h tends to 0 until you substitute h into the equation, right? So if I was left with at the bottom top of here like plus h, for instance, and then plus h, okay, now that wouldn't actually work out, but okay, let me just leave this out. But let me say, like, if I was left with a plus h over here, then all I do is I just take this 0 and then I substitute over here, and obviously that means that this term will no longer exist, right? And then I would still be in this exact same scenario over here. So I've got 2x plus 6, right? And then yeah, and then now I've got, so I can say now that my first derivative is equal to 2x plus 6. And if you are familiar with our differentiation rules, you can kind of check that for yourself, right? So make sure that when you in fact you should know your differentiation rules by the time you're doing your exam. So you know the first derivative of this, the derivative of this function, of this term would just be 2x, right? And then the derivative of this term would be simply 6, because this is 6x, would just be 6. So that makes sense. That's how you check. You should know your rules, right? So now I've got, yeah, so I know that this is correct. Now if I were to ask you for the first derivative, so if, let's say this was for this thing, obviously this is x squared plus 1, but let's imagine that this was referring to this particular parabola. If I were to say what is the first derivative at point B using first principles, so you first have to do all of this, and then once you reach to this point, then you substitute the x value of B over here, right? Because this line could have been anywhere, the tangent could have been calculated from anywhere. I'm asking you for the tangent specifically at point B, right? So the gradients of the tangents, in other words, specifically the gradients of the tangents to the curve, right? In other words, the first derivative, right? So I'm asking you for the first derivative specifically at point B using first principles. So you first have to do this whole first principle process. Once you've done this whole first principles process, then you're left with this particular line. Once you're left with this particular line, everywhere where you see an x, you substitute with a 2. So now I've got 2 multiplied by 2 plus 6. 2 times 2, that's 4. 4 plus 6, that's 10. Obviously, that's not accurate in this particular case because that was a different function. So it's x squared plus 6x plus 9. But the principles remain the same. And that concludes our video on using first principles in order to find the first derivative. If you found this video helpful, please be sure to like, subscribe, and obviously share this to anybody else who you think may benefit from this. And if you have any questions, anything else that you want us to cover in future sessions, be sure to write them in the comment section below. If you're interested in one-on-one sessions, obviously contact us over here. If you want to join us for group sessions as well, contact us over here. If you want access to the drive where we have a bunch of questions, us going through different questions in different sections of the paper. So for example, an entire video of 1 hour or plus of just going through all the algebra in paper 1, all the algebra, all the trigonometry questions, etc., etc. If you're interested in that, then just contact us for more details on how you can purchase that. And yeah, that concludes the video. And until next time.